Welcome to the FLUTE tutorial. Federated Learning is a distributed learning approach that brings model training processes to the training data. Federated Learning addresses some privacy and compliance concerns related to data curation, but introduces new challenges with respect to infrastructure, performance, and robustness. This video aims to help developers and researchers who are interested in building novel proof-of-concept federated learning solutions using FLUTE. During the following 20 minutes, we are going to explain our vision for FLUTE, the main architecture, a walkthrough of the relevant components, the prerequisites before implementing your machine learning model solution, and finally, a live demo of how to incorporate your machine learning model into a federated learning environment. We are assuming that you feel comfortable working with Python or PyTorch and have a good understanding about how federated learning algorithms work. However, this last point doesn't represent an obstacle for the developer side. Before continuing, we highly recommend you working on Linux or Windows and installing Anaconda and MPI beforehand so you can run smoothly on the last hands-on part of this video. While several open source frameworks have been developed to enable federated learning solutions, few offer end-to-end simulation. A simulation platform can play an important role in enabling researchers and developers to perform proof-of-concept implementations and validating their performance before building and deploying in the wild. The main goal of FLUTE is to be a high-performance simulation platform that allows quick prototyping for federated learning research. FLUTE has a number of characteristics that enables the user to prevent future scenarios before implementing the solution in a production framework, such as privacy tools, communication strategies, and scalability. FLUTE also provides an optional integration with Azure ML workspaces, enabling scenarios closer to real-world application and leveraging the platform features to manage and track experiment, parameter sweeps, and model snapshots. How does it work? Every time we execute FLUTE, we are launching a job that consists of one or more independent nodes that can be physical or virtual machines that can execute up to K workers, which are independent OS-level processes. A worker can be either a client or a server. During each iteration round, the orchestrator, which is the worker 0, dispatches the central model to the rest of the workers, and then queues up the client task for workers to execute. The workers receive the client task, which is basically the training data plus the configuration of the task, and execute stochastic gradient descent on the central model using the client training data. Once this is done, the client sends the pseudo gradients back to the orchestrator, where they will be aggregated. FLUTE uses the library of message passing interface, well known as OpenMPI, for its communication backbone, which is defined in federated.py. Once the server is instantiated, it acts as the orchestrator, which takes care of the following. Run an initial validation testing round if the options have been enabled in the configuration file. Set the initial learning rate for the workers. Sample the clients from the pool of available workers. Dispatching training tasks for all the sampled clients and receive back the pseudo gradients. Note that at this point we already have the pseudo gradients for each client, and they come with a specific weight that can vary accordingly if we are using DGA, which is dynamic gradient aggregation, or Fed average. Perform aggregation, and finally some run stat and profiling steps. Let's move on to client. All of the processes to compute the gradients that are delivered to the server happen here. Each independent client performs the following. Reads the configuration task. Prepares the client data that will be sampled for training. Initializes the model, optimizer, data loaders, and the scheduler. Performs several iterations of the training on the client's training data. Estimates the federated optimizer weights, such as DGA or Fed average. And finally, prepares model parameters to be transmitted back to the server. How do I build my federated learning solution using FLUTE? During the following section, we are going to explain what are the steps to follow in order to create our federated learning solution with FLUTE. First, we need to incorporate our machine learning model, previously framed in PyTorch. A clean and standard declaration of the machine learning model requires the following 5 functions inside the platform. First, the constructor, with the model definition and their respective layers. Second, the loss function that computes the loss that we are using during the training rounds. Third, the inference function that is used to perform the metrics used during evaluation rounds. And finally, the sets function that will bring the model into evaluation or training mode. The example shown in the screen was taken from the CNN classifier experiment in FLUTE. Second, data preprocessing. At the moment, FLUTE supports HDF5 and JSON formatted inputs and requires a specific format for the training data, which is a dictionary of the following: users, an array with a unique ID for each user ID in the training data; user data, a dictionary containing the user index training data in the form of a dictionary; number of samples, an array with the number of samples for each user in the same order of the user list; user data label, this can be optional, a dictionary with the same structure as user data containing the training data labels in the form of a dictionary. The format displayed on the screen is mandatory because of the design of FLUTE, but we provide some sample scripts for preprocessing the data into this format in Utils Preprocessing folder. The easiest way to start experimenting with the different features that FLUTE provides is through exploring the configuration file, while all the setup for the task are started. FLUTE config files have the following sections. First, model config contains the path and parameters if are needed to initialize the model. Second, dpconfig contains the differential privacy setup and can be disabled. Third, privacy metrics config. This is for cached data to compute additional metrics, can be disabled as well. Fourth, strategy. For choosing the federated optimizer we want to use, either DGA or Fed average for instance. Server config determines all the server-side settings. And finally, client config dictates the learning parameters for client-side model updates. In order to see which parameters can be used for each section, you can find fully documented examples inside the configs folder. Now that we have covered the basics for incorporating your machine learning model solution into a federated learning framework, let's move to the demo. During this last section, we will show you step by step how to run one of the tasks pre-configured in FLUTE, and we will demonstrate how each step described in the previous section was incorporated for this task.
Hi there. In this tutorial, you'll learn how to run your first federated experiment in FLUTE. For this, you're going to need three things installed in your computer: Git, Anaconda, and some implementation of MPI. We have tested both MPI for Windows on Windows and OpenMPI on Linux. During this tutorial, I'll first show you how to clone the FLUTE repository and how to install the required Python packages. Next, we'll take a closer look at one of the experiments we have implemented on the repository, where we train a classification model on the Cypher10 dataset. You'll see how model, data, and parameters are set for this experiment and how to actually run it in your computer. With this, are you ready to start? This is the website where you can find the FLUTE Git repository, github.com/microsoft/msrflute. Here you can see the README with the tail instructions. What we're going to do next is also described here. By clicking on code, you can find the URL that you use to clone the repository. We then proceed by typing git clone followed by this URL. Once the repository is cloned, you can cd into it. Inside, you'll find a file called requirements.txt. This file contains the list of Python packages you'll need to run FLUTE. We'll first create a new Anaconda environment called FLUTE. We'll use Python 3.8, which we know works well with FLUTE, but you can also try different versions. Finally, once the environment is created, we type conda activate FLUTE and then install the packages by running pip install -r requirements.txt. This will install a bunch of packages and might take some time, maybe around 5 or 10 minutes to conclude. In the meantime, we can take a look at how the experiment is specified in FLUTE. Here we have opened the FLUTE repository in VS Code. In the experiments folder, there are a few examples that you can use to create your first experiment. We're going to take a closer look at one of them, classifCNN. There are 3 or 4 important files that we should look at. The first is model.py, which specifies the model architecture. Here, we have a simple convolutional network with just a couple of convolutional layers. We'll wrap this model using a different class called CNN, which must specify 4 different methods: loss, inference, seteval, and settrain. Essentially, this tells FLUTE how one evaluates loss and output for this particular model. Let's now take a look at how the dataset and data loader are specified. We have 2 files inside the data loaders folder. Never mind the text prefix, this is just for practical purposes but will be removed eventually. Inside the dataset, we need to specify how the data of any given user, identified by user index, should be retrieved. We typically follow this structure for the data. We use either a JSON or HDF5 file with its 4 fields. Finally, the data loader simply wraps a PyTorch data loader, together with the collate function that builds batches with a specific format. The last file we need to look at is the config.yaml, which contains all parameters for the experiment, including what federated strategy is used, how many clients are processed at each iteration, the batch size, etc. The parameter names try to be self-explanatory, but there are also comments here describing them. Next, we'll see how to actually launch this experiment in your computer. First, we need to prepare the data. You need to first run the utils/download and convert data.py script. That will download the Cypher10 dataset and convert it to a HDF5 file in the expected format. We're going to split the 50,000 samples in CIFAR uniformly among 1,000 clients so that each has 50 samples. Looking at the utils/data folder, we can see that 2 HDF5 files were created, since I already ran the script beforehand. Finally, to launch the experiment, you can use the command that is available in the README. This is just calling MPI with 4 different threads. One of them is a server, and the other 3 workers that process clients. And then just calling Python with the E3 trainer, passing the data path, the output path, the config path, and the name of the task. You can see that the experiment is starting. It will first run an evaluation round. And then it starts processing clients. At any given iteration, it will process 10 clients, each with 50 samples. After 50 iterations, it will run another evaluation round. And we'll see it already has a reasonable number considering the network we're training is quite small. So here we can see that the validation accuracy is already 31% after 50 iterations.
We hope that developers and researchers can take advantage of this framework in the development of new federated learning efforts, and we encourage the research community to explore new approaches using FLUTE. For more information regarding FLUTE implementation, please visit our documentation. We also encourage you to check out our paper in arXiv. Finally, read our latest post on the Microsoft Research blog, where you can find more information about this project.